Okay, let's get started right away because I want to give you as much free time today to work on stuff as I can. We didn't finish the set of notes from the topic 4, and really topic 4 and 5 should really have gone together, but with you guys having missed yesterday for the car crush party program thing, I knew that we just needed to put a gap in between. So ideally, I would have just merged right from 4 to 5, but instead we'll just finish off the second half of 4 and we'll finish 5 tomorrow. So, historical context. We've gotten to the point where in 1900 Max Planck decides to, well, doesn't decide to, he discovers that energy is quantized and realizes that energy must come in minimum packets. And really this fundamentally revolutionizes the way that physicists look at things. And we've mostly been focusing this unit then on the models of the atom. The biggest change was 1909 when the Rutherford gold foil experiment is performed, and all of a sudden he has this epiphany that all of the mass must be centered in the nucleus. And that's what we're focusing on these next 2 days. This is topic 4 and topic 5, the idea of nuclear chemistry. And so I wanted to repick things up again here. I know we went a few slides past this, but I wanted to just make sure I did a good enough job of explaining how to calculate the energy found in a nucleus. I'd like to just redo this example one last time, make sure I did a good enough job. So, okay, so the nucleus is all protons, right? Well, not all protons, but it's protons and neutrons. James Chadwick didn't discover the neutron until later, but they knew that all the positive charge was centered in the nucleus. But shouldn't all those positive charges, shouldn't they want to repel each other? Shouldn't the nucleus just intuitively want to just break apart? Doesn't that make sense based on all the positives being there? And then further to that, shouldn't the electrons, by virtue of them being oppositely charged up to the nucleus, shouldn't they want to spiral into the nucleus? Now, we already kind of talked about that problem with Rutherford's model and the idea of energy levels. Maybe the electrons don't behave as matter. Maybe the electrons behave as a wave. Well, if the electrons behave as a wave, well, then maybe that solves the problem of the electrons wanting to spiral into the nucleus. So, I mean, that's not a bad idea. That's a good theory. I'm not sure that that's ever testable. That's one of the cool things about this physics that we're going to, right? Is that so much of it is just hypothetical, and maybe it will shake out to be kind of right but kind of wrong, and 50 years later we'll be learning something new. So, anyways, today I want to focus on that nucleus though, because I already gave some historical context. In the 1930s and 40s, the Manhattan Project. Maybe you recognize some of the names I mentioned: Enrico Fermi, Robert Oppenheimer, Albert Einstein. They were part of trying to basically harness nuclear energy and create nuclear bombs, right? You guys have heard of the, what was it called again? It was Los Alamos. It's where they were testing in New Mexico some of these nuclear weapons. So, anyways, that's what we're talking on right now, nuclear chemistry, which is really, it's physics and chemistry combined talking about the nucleus. And then here was this fundamental issue that Einstein was able to resolve. So here's the problem. If we count up all the individual pieces of protons, neutrons, and electrons and weigh their mass, but then we actually find the mass of the nucleus itself, they didn't equal. For some reason, individual pieces did not weigh the same as the collective sum of all of the whole. Does that make sense? And I had this analogy that to me it makes sense. Hopefully I did a good job of explaining it, but let me try again here. It's the idea of my daughter playing with Lego. And so when we buy Lego out of the box, none of the pieces are assembled. And if we were to weigh all of those pieces individually, you would think that once you make whatever car or Barbie dream house that you're making out of her Lego pieces, you'd think that all the individual pieces should weigh what the collective pieces weigh. They don't. Makes no sense, right? It's like, shouldn't there be a law of conservation of mass? Antoine Lavoisier proved that like in 1800 something. No. Individual pieces do not equal collective pieces. But this actually helped explain what we've now coined as the strong nuclear force. Einstein figured with his formula E equals mc squared that missing mass must be the energy used to keep those protons together, because otherwise they'd want to fly apart. And the analogy I gave is if I use super glue to kind of glue them together, maybe that's the missing mass. It's the energy to keep them together. Does that make sense so far? So I'd like to redo this example here before I move on here and find the mass defect in binding energy for magnesium-24. Now, on your data table, the only information that you have is the mass of the neutrons and the mass of the protons. And so in order to do this a little bit more precisely, I went and I actually printed off the one slide in your notes here that had this big table of selected masses of isotopes, and then on the side there were masses of atomic particles. You know what that slide is? So this would be to do it more precisely. I'm pointing this out because if you get this question on a test, they'd have to give you more data than what's in your data sheet. So let me just redo this to make sure I did a good job the first time. Magnesium-24 collectively, I can look it up on the sheet here, and magnesium-24 says that it weighs, and I'm going to try to get this proper this time, 23.985.042. That's how much the sheet says magnesium weighs when you put it all together. So far, so good? That, however, was in a unit called an atomic mass unit. So we would have to multiply by 1.66 times 10 to the minus, is it 27? The atomic mass unit? Okay. And this would be, I'll just call this A right here, because I don't want to do all the calculations, but this would be the collective mass of all the particles. Now, in theory, if you find them individually, the mass should be the same. It's actually not. But ideally, it should be the same. So the way we would do that is we would look at magnesium, and then on a periodic table, we'd say magnesium is number 12. So by virtue of that, it means that we have 12 protons, and we have 12 neutrons. Am I in your guys' way, by the way? You see past me? I feel like I'm more or less in your way. Let me move back. Consider that. And then you'd have to look up the mass of protons and neutrons wherever you'd find it. Now, they're on your data sheet, but on your data sheet, they only give you 3 sig digs, which is pretty typical, which means that I think they're both 1.67 times 10 to the minus 27. But if you look it up a little bit more precisely on the data sheet I've got right here, hopefully this is what we wrote down yesterday. It's basically 12 times, okay, the mass of a proton is 1.672622. And that's already in kilograms, so I don't have to convert it. And then the mass of your neutron is 1.674927. And I'm just going to write it like this. It's a little different than what we did last day, but see how there's 12 for both of them? I'm going to factor out the 12. I'm going to add the two masses together, then times by 12. And then long story short, that should give you an individual mass. These did not equal each other. Einstein theorized then in E equals mc squared that that missing mass was actually found in the form of energy. And energy was then being used to help keep the nucleus together. So if you took these numbers and you subtracted them, then that was known as the mass defect. And then if you took that mass and put it into E equals mc squared, that told you how much energy must be needed to bind. You guys able to follow that? So hopefully I did a better job today here of kind of illustrating the concept. If you're asked to do this, most of the information you're going to be getting off of a table. Okay, it's not coming out of your data book. They'll have to give you some extra table. Yes. Yeah, a common misconception is the thought that that the M is the total mass of the molecule and that all of the mass of your nucleus converts into energy. But that's not the way it works. It's the missing quote unquote mass that must have been energy. That makes sense? So, anyways, when we found that energy, I wanted to point out a couple of things, and hopefully I did a good enough job of this on Monday. That energy was like times 10 to the minus 11 or 13 or somewhere in that ballpark. Do you guys have that value written down? How much was it? Okay, 11, which doesn't seem like all that much, right? In the grand scheme of things, you think, wow, that's a small amount of energy, but that's for one nucleus. Right? And then so when you start considering the scale of this, if that's how much energy it takes to bind one nucleus, if we were to times it by, hypothetically, let's say Avogadro's number, 6.02 times 10 to the 23, that's how many molecules are in a mole, right? Well, if you were to do that, then all of a sudden, then we got like a huge amount of energy. And that was just for 1 mole worth of stuff. Chances are we're not working with just 1 mole. We're probably working with 2 or 3 or 10 moles of stuff, right? So it's a huge amount of energy. Hence the whole 1930s, 40s initiative to say that we can harness nuclear energy. And I mean, we're still using that to this day, right? Now, there are some downsides to nuclear energy, though. And that's where the second half of the lesson kind of needed to go to, is that nuclear energy gives off different types of radiation. And so this is kind of where I got to last day, and then I was starting to rush at the end, so I want to make sure I do a thorough job here. There are 3 types of nuclear radiation that are then given off over the course of some sort of radioactive manipulation. Maybe you've heard the word before called transmutation. Have you ever heard that word before? It sounds really sci-fi, transmutation. Anybody know what it means? Exactly, yeah. Back in medieval times, sorcerers and magicians were trying to do transmutation. I don't know if I've ever told you the story before, but they were trying to create gold. Ever told you this story? And they were trying to turn lead into gold. If you look at the periodic table, lead is number 82, and gold is number 79. And so lead, very dense, quite abundant. Gold, very rare, very valuable, right? They're actually not really that similar. Actually, gold is kind of a very thin and pliable and ductile, shiny, gold-colored metal, whereas lead is a lot more dense. It's a lot more thick. We make like our radioactive our shielding for X-rays out of lead, right? But the idea was, well, let's try to transmutate the lead into gold by removing 1, 2, 3. If we removed 3 protons from the nucleus, that would do it. Right? Now, back in sorcery, medieval alchemy type of times, they weren't able to actually do that. That was just magical, wishful thinking. But it actually was discovered. One of the first people who started working on this was actually Ernest Rutherford. I was doing some research on him just to kind of prep for the lesson. He actually won the Nobel Prize in 1908 for his work on radioactivity, which is kind of funny because we know him for his gold foil experiment, which he did 1 year later, but he actually won the Nobel Prize before that for different chemistry work on discovering radioactiveness and the idea that you actually can change the amount of protons in a nucleus. And so this transmutation can occur through the radioactive decay that we've got right here. So here's the 3 main types. You've got alpha, beta, and gamma, and he named them just basically off Greek letters on the Greek alphabet. I think in hindsight he should have maybe named it after himself or something, because that's what a good scientist does, right? They name it after themselves. Okay, so to recap here, here's alpha decay. Alpha decay occurs when the energy within a nucleus shifts and it spits out an alpha particle. Now, an alpha particle is using this notation, so that little alpha fish symbol with a 4 and a 2. But if I wasn't clear on this yesterday, basically this is helium. An alpha particle is helium minus the electrons. And to be honest, the electrons weigh so little, we usually skip them anyways. Okay, but a true alpha particle, 2 protons, 2 nucleus. And so all of a sudden, all of this matter, this nucleus, you know how normally it does? We talked about how those protons, there's so many of them shoved in there, they wouldn't want to be there. They'd want to separate. Well, there are some atoms that are radioactive where they're unstable. The nucleus is not able to handle having this many protons all together. And so eventually it will get kicked out. I mean, if you can imagine this analogy, it's like there's, here's our room. Our room is the nucleus right now. And all of us are protons. So we've got, I don't know, what do we got, 11 of you with me here? 11 protons, very stable. We can handle 11 protons. But what happens if it were uranium, which is the radioactive material? Uranium's number 92. 92 protons. If there were 92 of us shoved in this room, that wouldn't be as comfortable, right? We'd all want to have our own little space. I don't necessarily want to get and so we spread out, just like protons would want to do. If we shove 92 of us in here, that wouldn't be very stable, right? And so eventually what the nucleus does is it just boots out 2. It kicks out 2 of the neutrons. And what also ends up happening, though, is it releases huge amounts of energy, right? Because remember how there's that energy that's being used to bind the nucleus together? If we separate out that nucleus, energy gets released. And so one of the things that occurs is in the alpha decay. In terms of terminology, the parent nucleus is the original, and then we use the word the daughter nucleus to describe what is happening after 2 protons and 2 neutrons are kicked out. So I believe we did this one last day, but let's just do it one last time here. If you have alpha decay for iridium, this would be 168 as the total number of nucleons. You guys know the word nucleon? Particle out of the nucleus, so proton or neutron. Iridium was, what number was it again? 77? Sure, okay, 77. So then if you're going to have alpha decay, what ends up happening is the iridium loses 4 nucleons, which involves 2 protons and 2 neutrons. And in doing so, it transmutated itself into a new element that's now a 75. Because really, this 77 loses 2 to become 75. This is why you just need a really basic periodic table. Like all you'll get on your diploma is just, it gives you all the elements and it gives you all the numbers and that's it. That's really all you need. So you just have to look at the table and figure out, well, who's 75? Re, whatever that is. Rhonium, something like that. And then, I mean, just so long as you can do some basic math, 168 minus 4 gives you 164. I remember a couple of diploma questions, if I could describe them to you about this. A couple of them were numeric response, where what they did is they gave you a basic equation here, and what they did is they left these numbers or these numbers here blank, for example. I see yogurt, bananas, and apples. Good luck. Okay, I think they're good. Make sure. On the diploma question, one of the ways I saw them phrase this is that they wrote it, but like they left like this spot right here, or say this spot right here blank, and then you had to just use some common sense, I guess, some basic addition skills, and then make it like numeric response and fill in the blank and say, okay, well, if this was 75 and there's 2 here, this must be 77. You know what I'm saying there? So I also saw one where it was numeric response and it was like a matching one where they gave a whole bunch of different possibilities. So they'd say, if iridium undergoes alpha decay, what does it make? And it might have been like, say, a 164, 75 Re. That's the right answer. But they could have given like a 168, 75 Re as a distractor, or a 164, 73 Re, or a 164, 70, 75. And maybe not, rather than picking Re, they might pick, what's next to it? O. And they might give you a whole bunch of different distractors where maybe they'd screw up by having the wrong number on the top or the bottom. Maybe they would screw up by putting the wrong element in the spot there. And it was numeric response, so you had to like match and say, well, 1 is this one, or 2 is this one, or 3 is this one, or 4 is this one. You had to match and figure out what it was going to create. Does that make sense? So, long story short, so long as you can basically add up the nucleons across the top and the bottom, you're good to go. Right? Which is more or less a law of conservation of mass again. You have to have the same number of the total top number and the same number of the total bottom number. So, the other thing they might ask you to do is figure out how much energy is released. And so this is another question where I felt like maybe I rushed through this a little bit too much. Basically, the idea is you want to figure out how much mass you had before. You want to figure out how much mass you have after, and they're not going to equal each other. Why are they not going to equal each other? Energy was released, right? That strong nuclear force was help binding all those protons together. But as soon as 2 of them were kicked out, it also kicked out some energy as well, right? Using E equals mc squared. So all you've got to do is look up how much mass uranium has. You have to look up how much mass an alpha particle has. And you have to look up how much mass whatever the alpha decay was. So if this is 230, oh, I screwed this up. That's not how you write it. 238 and 92. This would be 234 and 90. Which that is a R something. Oh, no, thallium. All you'd have to do then is look this guy up on the table, look this guy up on the table, look this guy up on the table, and find their masses. Okay. Now, I think I lost a few of you last day. You can find uranium on the table that I gave you here. You can find thallium on the table that I gave you here, but there's no alpha particle. But that's not true. Do you guys remember where you found the alpha particle information from? Helium, yeah. So if they don't give you an alpha particle, use the helium nucleus instead. And basically just find this one, and find this one. And then when you have that information, then you subtract. That gives you the lost mass, the mass defect. And then that's the amount that you convert to energy. So make sure it's really clear here. The mass you use is not the total mass. That's not how Einstein's formula works. It's not the total mass times the speed of light squared. It's the change in mass, the lost mass. That lost mass is actually in the form of energy. That makes sense? Okay. I think that's about as far as I got, because then I was really rushing when I got to the next one. So let me take her from here then. That last bit of stuff should have been review more or less. Let's start from here. This is known as the second type of decay. This is a beta decay. This one's really strange. What ends up happening is a neutron basically splits itself into two pieces. When I think of a neutron, I kind of assumed that it was just a standalone particle. But apparently a neutron is really a proton and electron, which kind of makes sense because a proton's a plus one, an electron's a minus one. Put them back together, it's neutral. And if you actually take a look at the masses, if you guys have your table here, if you can go back a few slides, see how the mass of a neutron is just slightly more than the mass of a proton? I've got it in front of me. The mass of a neutron is 1674, and the mass of a proton is 1672. Why is the neutron weigh just a little bit more? Well, maybe it's because a neutron is really an electron and a proton shoved together, right? And so if you take the proton and add a little bit more mass to the electron, now you have yourself a neutron. So what ends up happening in this beta decay is that the neutron actually becomes a proton and an electron. And so this sort of transmutation, rather than actually losing a proton out of your nucleus, you actually gain a proton out of your nucleus. That makes sense? So what we end up doing here is calling that, where is it right here? The beta decay, we actually give it a special symbol. We use this right here. It's a fancy looking B. It's the Greek symbol for beta. And then we put a 0 on top and a -1 on the bottom, which I think actually makes a lot of intuitive sense because the top number is how much mass it has. But if this is an electron, we consider the electron to really not have any mass in the grand scheme of things. And then the bottom number is how many protons you have, which essentially is its charge. But an electron doesn't have a positive charge, it has a negative charge. So we give this symbol to describe we use it to describe a beta particle, but really a beta particle is an electron. So that's essentially what happens. A neutron turns into a proton and a beta particle, and then this is where I don't think I had nearly enough time to start describing this. Plus it spits out this thing, V. And this is going to be what we talk about in our very, very last topic. These are known as like the quarks and like the really, really small stuff, the stuff that we think makes up our fundamental particles. Okay. Basically, the theory is that protons, neutrons, and electrons are not as small as it gets. The idea is that there's even smaller stuff than that, and this is what's known as an antineutrino. Now, an antineutrino is basically the antimatter equivalent of what's known as a neutrino, and they're like even smaller particles than protons, neutrons, and electrons. Now, I don't want to like spoil this too much because I really do want to do this in sequence, but basically the concept is that there's matter and there's antimatter. I've already kind of described this idea before. When I think of antimatter, I think of like the bad Spanish doppelganger of someone who's got like a bad mustache. There's good Chris, and then there's like his evil twin Chris, right? And that's like matter and antimatter. And the theory is that whenever matter and antimatter collide, they actually release energy and destroy themselves. Crazy, crazy weird stuff. So anyways, I actually have a little slide here describing that, where we've actually discovered these particles. There's an electron, and then the electron has a positive doppelganger called a positron, which is basically the same mass as an electron, only rather than being negatively charged, it's positively charged. There's a proton. There's also an antiproton. There's a neutron. I don't know how this one works because a neutron's neutral, but there's apparently an antineutron. So, anyways, to get back to this one right here, apparently what ends up happening in this decay is that it also releases a very, very small neutral particle called an antineutrino. And it's like another piece that's there. Now, the antineutrino is so small that it doesn't really count for mass. So in terms of like when we want to consider its mass, we consider it to be like a part of a neutron. So in a way, a neutron is actually made up of three things at least. There's a proton and a neutron, there's an electron and a neutron, and there's an antineutrino and an electron. And these are like the subatomic particles known as quarks. On your data sheet, there's actually a little section where it talks about some of these things. I'm going to stand next to Baron here just because you have yours there. Can you guys see those ones? They're called first generation fermions. So it actually lists some of them There's the electron, then there's the positron. There's the electron neutrino, the electron antineutrino, and then there's also things known as the up and down quarks and antiquarks. And there's even smaller stuff than that, they figured. And you can see for some of these things here, they have like either partial charges or they have really, really small masses. I'll talk more about that later, about how the mass is measured in mega electron volts over the speed of light. But it basically has to do with E equals mc squared formula. So, anyways, hopefully I've given you enough that you can at least memorize the information right now. This is beta decay. It's very strange. So it's also possible to have what's known as beta positive decay. And what ends up happening here is a positron gets emitted. So rather than a neutron converting itself into a proton and electron, what can happen is a proton can convert itself into a neutron and a positive electron. Very, very strange stuff. But doesn't this make sense, though? A proton is positive. If it spits out a neutron, that doesn't change its charge. So if it's going to spit out the neutron here, then this particle right here must also be a positive particle. So it can actually spit out the positive version of the electron. And actually what ends up happening is then it actually releases the regular neutrino rather than the anti-neutrino. Very weird. So let's do an example here. Let's try to figure out the beta decay of thorium-238. Did we start this one? Like just barely though, right? Like this is kind of when I was rushing at the end. So let's try this one here. Thorium-238 is going to undergo beta decay. Sorry, that's 234. Okay, so thorium, we need to know its number. I think it's 90. Just need a basic periodic table to look at. Okay, if it's going to undergo beta decay, it's going to spit out. Now, if it undergoes regular beta decay, it spits out an electron. If it undergoes positive beta decay, it spits out an anti-electron, the positron. So this one here is going to spit out a beta particle. So one possibility for like how you could be tested on the question is they could leave this as X, and they could ask you, what is this number, and what is this number right here going to be? So what's the top number going to be? Yeah, it doesn't change, right? Because under this particular version right here, this guy right here, it just loses an electron. That doesn't really change its mass number because electrons they weigh so little in comparison. Okay. But what ended up happening is it spit out a neutron and it changed it into an extra proton. So this number right here would go up to 91. Does that make sense? So one way I've seen them test on this is they just leave these blank as a numeric response, and they ask you to fill in the blanks here. Okay. Really, this is the law of conservation of of subatomic particles. Right? This and this better equal this. Well, I left this as X though, but we shouldn't leave it as X. We should actually know what species it is. Number 91 is PA, whatever the heck PA is. I mean, you're working with some of this really strange elements here. So there, it would do that. Plus, in case they're being really picky, don't forget it also releases that anti-neutrino. So this is the equation for beta decay. 234 thorium 90 releases this particle right here, this one right here, plus the antineutrino. Now, if we want to figure out how much released energy there's going to be, we need to, again, go back to a sheet like this. So we would need to find thorium-234. So let me write the mass out here. Thorium-234 is 234.043601. So far, so good. Then, if I look this guy up in the book as well, proactinium is 234.043308. one more thing I should do. I should also consider, even though I know it's pretty negligible, let's find the mass of that electron as well. And so the mass of the electron is 911, but I'm going to look it up exactly here. The mass of the electron on this particle is 9.109383 times 10 to the minus 31. But if you have the same table as me here, it also gave you the electron in the amount of U's. And so I have that number right here. It's also 5.485799 times 10 to the minus 4. And the reason I chose that one is now all of these numbers are now in U units, the atomic mass unit value. So all of these numbers I had to look up, like they were found on a table. So in theory, this should equal those. Okay, so add the right-hand side up, 234.043308 plus 5.485799 E minus 4. It hardly makes a difference, but it makes a little bit of a difference. It makes it 234.0438566. You guys able to calculate that along with me here? I've been skipping units here. I'm going to throw the U on both of these. Which side weighs more? The left side. Which, you have to think quite cleverly about this, though. How did we end up getting more mass? Well, the reason why is that the left-hand side over there, the original thorium, it actually had more mass than that. It had some energy binding the nucleons together. And that energy was then released. So when we subtract these two amounts, this guy right here should have actually had more mass, because really, this guy should have had some energy binding it together. And that energy was then released. Is it able to follow what I'm saying here? This side right here weighs a little bit more than this guy right here, because this guy has a little bit of extra mass on it in the form of energy binding it together. That's where that missing mass happens to be. So I'm going to subtract these two numbers, and it's going to be really small, right? If I subtract, I'm going to get 238.043601. I ended up getting a difference in mass. The mass defect was 2.555799 E minus 4 of that unit there. An incredibly small amount of mass. I have 2.55. That's a point there. Anybody else calculate the same thing as me? Just to confirm. Anybody else get the same thing? You did? Okay. I just want to make sure I didn't screw it up. Okay. So now this, though, is in U. So if we want to find our energy, we're going to have to take this number here. I'll just call this A, if that's okay. We're going to have to times it by 1.66 times 10 to the minus 27 to convert it into kilograms. And then we'll times it by 3 times 10 to the 8 squared. And that'll give us how much energy we have. So to figure out how much energy we need, this number times by 1.66 to convert it into kilograms. So a very, very small amount of kilograms. And then also times by the speed of light squared. I got this. Let me know if you don't. E equaled 3.82, let's call it, times 10 to the minus 14 joules. Anybody else get that value? Here, I want to snake the data sheet. Okay, now there's a chance that they might ask you to use a different energy unit. They might ask you to use what's known as a mega electron volt. And I was hoping that there was an equivalency directly on your table, but there's not, unfortunately. So I'm going to have to explain how to get to there. Normally I measure things in joules. But there's another unit for joules on your formula sheet. It's just not directly there. It's that 1 joule. Oh, it's on the set here. You guys see there? An electron volt is an elementary charge worth of joules. You guys see that equivalency on there? It's 1 electron volt equaled 1.6. Yeah.
Does the anti-neutrino have a negative mass, or is that still a positive?
Really, let's just leave the mass off there and consider it to be so small that it's negligible. I don't fully get the whole positive neg.
Would it make the right side way left?
Oh, like if it had a negative mass? Yeah. I don't know exactly how they consider the masses of the antimatter to work. Like that's beyond what I actually understand. But it's an interesting thought. We should look into it some more. But from what I understand, the amount, even if it was a negative amount, it would be so small, like where this electron was right here. Here's what I do know. This electron amount right here, the antineutrino, its mass would be even smaller than that. So like as insignificant as the electron was, this guy would be like orders of magnitude even smaller than that. So it may actually add to the mass and make it a little bit bigger on the other side there, but not enough that would matter in our calculations. Yeah, it's something we should look into, though. It's not something I know nearly enough about this whole antimatter stuff. It's very, very high-level stuff. Good question. Okay. This is an electron volt. It's a very, very small unit of energies. This was essentially, the idea was this was the smallest amount of, this could be like the smallest amount of energy possible, an electron volt. So a mega electron volt is just times 10 to the 6 of those. So here's what we'd have to do. We'd have to take this number right here, and we'd have to times by 1 electron volt for every 1.6 times 10 to the minus 19 joules. You guys see how I'm able to cancel that there? This would then cause your joules to cancel, and you'd get into the unit of electron volts, which is a unit of energy. So divide your answer by 1.6 times 10 to the minus 19. And then what I'd have now is 238,647. That's how many electron volts you'd have. An electron volt is a very, very small amount of energy, kind of like Planck's idea, right? But if you want to have a mega electron volt is like 6 orders of magnitude bigger. So you almost have to drop the decimal place down then 1, 2, 3, 4, 5, 6. So the correct answer here would be like 0.2. How many sig digs do we get actually? I guess based on our data sheet, we were using a lot of significant digits. Why don't we just round it to 3 sig digs? Let's go with 239. That's how many mega electron volts you would have, and that's an energy amount. So the reason I wanted to point this slide out here is that not only are you using the E equals mc squared, the mass deficiency formula, but you may also get asked to find a mass or an energy in mega electron volts, and that's another unit to use. So, you guys think you can make that conversion? Divide by 1.6 to minus 19, but then to make it a mega electron volt, then hack off 6 zeros. Okay, third type of decay. Now, this third one right here is actually, when we talk about the energy that gets released, this is actually the energy that typically gets released. In the alpha decay and in the beta decay, there's that energy that gets released. But what ends up happening is the nucleus has now radically changed. It needs to be adjusted. Right? All of a sudden, you had all of your protons all shoved together. And what ends up happening is you either lost 2 protons or you gained a proton. Either way, at a nuclear level, that needs to shift around a bit somehow, right? And the shifting of this causes charged particles to move. Well, what do we know about charged particles that accelerate? They release EMR. And so it actually releases the EMR as a wave, not just as like just how much energy it has in joules, but this releases a secondary wave, and this is gamma radiation. So gamma radiation is also given off after either alpha or beta decay takes place. So I actually have a typo here though. It takes place after an alpha or beta decay. So after alpha decay occurs and that energy is released, well, then an EMR wave is also released by a shifting nucleus. Or after a neutron converts to a proton in beta decay, after that energy is released, there's also, in addition, gamma given off. Does that make sense? And so here's a picture that hopefully can describe things here. Here, this is what we just did here. Thorium gives off its electron, its beta particle. It turns into whatever this one was again. However, these protons and neutrons, they have to like shift around. They have to adjust themselves. Now, the number stays 234 and 91 right here. Nothing changed here. But as these guys moved around and shifted around, it gives off gamma radiation, which is actually very dangerous to you because gamma radiation can actually go through lead shielding. And so when radioactive decay occurs, it's not the alpha particle that kills you. Alpha particles are big. They'll just be stopped by paper. It's not beta particles that hurt you. Those are just electrons. That's not going to hurt you. But it's the shifting of the nucleus that releases gamma radiation. That's what causes a huge problem. Here's one more thing. It actually can't be deflected by a magnetic field. And here's, I'm going to skip ahead to this picture here, and then I'll go back to the one I skipped if you don't mind here. Here's a picture that I can explain why. An alpha particle is positively charged. Well, if you were to have a positively charged particle, I'm going to go up to the screen here, and you were to go into a magnetic field, a positive particle means use your right hand. If it were to come out of the box like this, upwards with my thumb, and I were to point my fingers into the field, you see how a positively alpha particle could be deflected that way using our hand rule? This is an electron. It's negatively charged. Use your left hand. Again, it's coming out of the box. If the field was going into the page, the magnetic field would actually cause the beta particle to deflect that way. But gamma particles, gamma radiation, it's not really well, I mean, we've talked about wave-particle duality, but it's not a particle that's charged. It's a wave, right? This gamma particle is really a wave. And we know that waves can act like particles and particles like waves, so I mean, sure, let's call it a particle if we want to, but keep in mind it's really a wavelength. This is the highest frequency wavelength possible. It's not charged though. By virtue of it not being charged, it actually wouldn't be deflected by a field. Does that make sense? So that's an easy way to test. That's also a test question I remember seeing before in the past. They might ask you, how do you tell the difference between alpha, beta, and gamma? Put it in a magnetic field. One deflects left, one deflects right, one doesn't deflect. So they could actually give you a test question where they show you a picture, but they don't tell you which one is which. And they might ask you to match. They might say, well, which one was which? So, okay, let me go back to this picture I skipped here then. So just to make sure I'm clear as to how this works here, you've got your regular nucleus. Let's say alpha decay takes place. Well, alpha decay spits out 2 and 2. Let's say that beta decay takes place. It spits out an electron. It really converts a neutron to a proton. But in either of these cases right here, the other possibility is a wave can be released. And that's as these particles here, as they shift themselves around to make it more stable. And it may not actually stay stable. It's actually possible for you to have multiple decays, where first this guy spits out one of these, and then it's still not stable. It spits out another alpha particle, and then it spits out a beta particle, and then it spits out another alpha particle. It's actually possible to have what's known as a decay series, which I'm sure, oh, good, it's my next slide. A decay series, go ahead. Yeah, until it finds a stable nucleus where it's finally okay with the proton configuration. Yeah. So there are certain things that are just, they're radioactive elements, right? Uranium is a good example of one. Plutonium's another one. Those are radioactive, where they are not very stable. They want to lose things out of their nucleus. They keep losing particles out of it and emitting off energy until finally it finds something that it's okay with. So here's a series then. Thorium turns into radium. Then radium turns into actinium. And then actinium turns into francium. And then francium turns into astatine. And then finally it stops. But in the meantime, a whole bunch of stuff has happened. You've lost an alpha particle. And then you lost an electron. And technically that's a neutrino. And then you lost another alpha particle. And then you lost another alpha particle. But finally, after all of this, finally the decaying is finally stopped. And it reaches this spot right here where it's finally done, quote unquote, because this is now stable. That makes sense? Okay, now this whole radioactive decay then, this is kind of the third set of things I need to talk about. So I kind of mentioned on Monday that I need to break this lesson up into chunks. I think the first chunk would have been talking just about the idea about how E equals mc squared, how that mass defect is there. Second chunk, I need to talk a little bit about how the nucleus itself can undergo the alpha, beta, and gamma decaying. The third section here is relating to math now. There's actually an exponential pattern to this, where you can actually have an exponential graph that comes down, and you guys know the asymptote concept, right? And you've done this in 30-2, right? The idea of an asymptote. We can actually plot an exponential decaying graph here, which fits the formula y equals a b to the x, some sort of like exponential graph equation. And there's actually a formula on your data sheet about this. I believe it's n equals no times 1/2 to the power of, I don't know, help me out here. You guys see that last question? Just n? Okay. There's one last equation. This is like the last one we haven't covered. And this is more or less an exponential equation where we've discovered that stuff always seems to cut in half every certain amount of time. So for example, carbon-12 decays every 5,700 years. In 5,700 years, it'll finally have got its nucleus will have decayed and cut itself in half in this amount of time. And so slowly over time, the amount that you have will decrease according to an exponential pattern. So, like here's a picture that kind of describes the idea. Let's say that right when you begin, you have 100 atoms. Well, after 5,000 years, you'll be down to 50 atoms left. All the rest of them will have decayed to something else. Well, then after 11,000 years, of those 50 atoms, well, 25 of them will be left because the other 25 decayed to something else, and so on and so on and so on. But you get yourself to a point where eventually there's still a little bit left, because, I mean, when you cut it in half and you cut it in half again, you technically never reach zero. That's that whole asymptote concept. So anyways, we can measure this with a Geiger counter. If you guys have ever seen these before, they basically measure how much radioactivity there is. It's how much it decays every second. So here's what you need to be able to do. You need to be able to use this formula. Okay. Now, I'll show you guys a couple of different options. There's an option using a graphing calculator, and if you guys know how to use logarithms, we can do that as well. So I'm going to give you guys basically a really quick crash course in Math 30-1. So let's do an example. Let's say that you have some lead-212. Lead-212 is going to decay. Now, I don't care whether it decays by alpha, beta, or gamma. It really doesn't matter. But let's say that it's going to slowly but surely decay because it's radioactive, and it's going to turn into, I don't know, maybe it'll turn into mercury. It'll undergo alpha decay. Maybe it'll turn into bismuth, and it'll go beta decay. I don't really care. But it's going to decay. And you start off with 75 grams. Well, slowly over time, the amount of lead that you have is going to decrease until there's only 9.3 grams left. So if you want to use that formula I just showed you there, N equals NO times 1/2 to the power of N. That's the formula? There it is. We want to figure out how long it takes until there's only 9.3 grams left. What we really have to do is figure out how many half-lives it's going to undergo. So if I want to throw some numbers into the equation, we're eventually going to have 9.3 grams. And 0, though, is how much we had when we started. So when we started with 75. And this thing got cut in half over and over and over again. And what I'm not sure about is how many times did it get cut in half over and over and over again. So what we're really doing is we're looking for the exponent. Okay, now here's one option. Let me grab a calculator. This is the least effective option, but it doesn't hurt to try this first. Take 75 and divide by 2. Okay, so there it got cut in half once. Divide by 2 again. Now it's got cut in half a second time. Divide by 2 another time. Look, there's my 9.3 essentially. So how many times did this thing get cut in half? It got cut in half one time, 2 times, 3 times. So essentially what that means is that this end up here in the corner was 3. It got cut in half 3 times. 75, cut in half once, cut in half twice, cut in half a third time works. That's one option. Another option is you can use logarithms. So if you know how to use logarithms, you could do this. You could take the log of 9.3, and then you could take the log of 75 times 1/2 to the x. Now, if you know your logarithm rules, which, okay, you guys just have to bear with me on this. This is a crash course. You don't have to do it this way, but if you can follow this, feel free. Okay. There's a logarithm rule that says that when you're taking the logarithm of two things that are times by each other, you can separate it by half. So what I could do right here is make this the log of 9.3 still, and I can make a log of 75, and I can add a log of 1/2 to the power of x. Remember your log rules? These two things are being multiplied, so I can take a log of each of them individually and add. Now, you still have your x up here as an exponent, but there was another log rule we learned, which I'm going to talk about. You can drop the exponent down in front, which means you can make it x log 1/2 and get rid of having an exponent altogether. Okay, the last thing you need to do is isolate for x. So the way you do that is you take the log of 9.3, you'd subtract the log of 75, because you're going to bring this number to the other side, and then you're going to divide by the log of 1/2, and that will get you x by itself. If you know how to use your logarithm rules, it's an option. If you guys don't get my quick crash course, don't worry about it. I'll show you other ways. So, anyways, if I grab my calculator now, let's try this. It was the log of 9.3 minus the log of 75. And then after I do that, I have to divide by the log of 1/2. Basically, give me 3. Only a little more precise than 3. Remember how when I was just doing it by hand, and I said, well, 75 divided by 2, divide by 2, divide by 2, and I figured it got cut in half 3 times? It actually didn't get cut in half quite 3 times. It got cut in half 3.011 times. But that'll work essentially. What I've now solved for is that my n, the number of times it's got cut in half, it got cut in half 3 times. But that's not where I'm done though, because I've still got one more thing to do. It says that it has a half-life of 10.6 hours, which means every time it gets cut in half, it takes 10.6 hours. How many times did it keep getting cut in half though? Well, 3 times worth it got cut in half. So I got to take this number and times by the 10.6 hours. Only to do it even more precisely, I'm going to take this number and I'm going to say it got cut in half this many times. And each time that it gets cut in half, it takes 10.6 hours to do so. So the total amount of time it's going to take is 31.9 hours. And because I only get 2 sig digs, let's call it 32 hours. So to use this formula here, you need to solve for the exponent up in the corner and figure out how many times is it going to get cut in half. We probably could have just done it by hand and just said, oh, look, it got cut in half about 3 times. There's one more option here. The other option is you could actually graphically solve it. You could say we want it to eventually be 9.3. Originally it was 75 being times by 1/2 to an unknown exponent, and you could find where this thing intersects. So I'm going to just make my window size go from 0. I'm going to make my x max, though. I'm going to make my y max go from 0 to 75. Why am I going to make my y max go as high as 75? That's where I started, yeah. 75 grams is how much total initial amount of nuclei I had, and they slowly transmutated to something else and something else and something else. But 75 grams is how much I started with, and eventually it's going to run out. So if I graph this, here's where it's 9.3, and then this is an exponential decay graph. If I were to find where these things were to intersect, I would discover that for it to get down to 9.3, it took 3 different sets of cutting in half. So it cut it in half once, that took 10 hours. It cut it in half again, that took 10 hours. It cut it in half again, it took 10 more hours. Does that make sense? And that's why it took about 32 hours by the time we were done. You guys able to follow that? I'll show you guys some more examples, especially the guys in grade 11. I'll show you more examples of how to solve these ones. It's pretty much the only math we do in this entire unit, is this formula here. Well, minus E equals MC squared. Okay, does that end your notes, or do you guys get these practice diploma ones? That ends them. Okay, so I've got 20 minutes left. Why don't we try some practice diploma questions on this concept together as a group, just to make sure you guys make sure that it's solidified. So, 3 things you should know how to do, though. First thing, you should get the concept that there's a mass defect at a nuclear level. There's more mass individually than collectively, because collectively that mass is found in the form of energy, and that energy then gets released in order to separate the molecules. 2, you should know the 3 different types, alpha, beta, and gamma. Either lose an alpha, gain a proton by losing an electron, or usually what happens in either of these cases, as the nucleus shifts, it releases EMR. And then the third thing, can you do the math behind half-life? So let's try this question set here. I'll just read it out for you here. In nuclear power stations, they use uranium-235. And it tells you that uranium-235 spontaneously decays to produce thorium-231 plus another particle. I'm just going to pause here. What is one of the other particles that's produced? Well, how do you get from 235 down to a 231? How many nucleons did you lose? 4. Well, if you lose 4 nucleons, what did you lose? You lost an alpha particle. Right? Because really, thorium-231 is thorium-231 with a 90. So the 92 went down to 90 by losing 2 protons. So it's alpha decay that's happening. Okay. Follow-up question. They then said, well, how long would it take for 10 grams to get down to 1.25 grams in the nuclear reactor? So let's use our formula. It basically says you're going to want to end up with 1.25 grams. We started with 10 grams. It got cut in half over and over again an unknown amount of time. Now, unless we have to be really, really picky about this, this is probably the best option. I'll say, well, 10 gets cut in half once, gets cut in half a second time, gets cut in half a third time. Okay. How many times does it take for it to decay? We say it has 3 half-lives. So it took 3 sections for it to decay. So long story short is our n is 3. Well, how long does it take? It says that 1 half-life, for it to get cut in half once, it takes this many years. So what do I have to do to get my final answer? Times this number by 3. So 7 times 10 to the 8 times by 3 half-lives is that number, which is probably 21 to the 9. Okay, different question here. We've got 1.6 times 10 to the 3 years is our half-life. 20 milligrams is going to decay down to 2.5. How long will that take? Again, really similar concept, right? we're going to want to finish with 2.5. We started with 20, and it gets cut in half over and over again an unknown number of times. So I would start by doing this every time. 20 cut in half. That's once. Well, that's not half. 20 cut in half is once. Cut in half again is twice. Cut in half again 3 times. As long as it's like a whole number, don't worry about using logarithms or your graphing calculator. That's not really necessary. Just keep dividing it in half over and over again. So, again, it took 3 times for this one to occur. I mean, really, it's either got to be 1 or 2 or 3 or 4 probably, right? And then it takes this many years for it to get cut in half. So 1.6 times 3 is going to be 4.8. Easy enough. Okay. New piece of wood, radioactive decay rate of carbon-14 is 816 decays per hour per gram. That's an extra little twist we haven't had before. Might just be there to throw you off. Again, it tells you the half-life of carbon-14. And then actually, here's what we're looking for. It says the decay rate of carbon-14 in our archaeological wood artifact is 12.75 decays per hour per gram. It's a different unit type, but we can still use the same formula. When we started, there were 816 decays per hour per gram. But many, many, many years later, the amount of decays per hour per gram is finally down to 12.75. It's the same concept, right? So, how long does it take 816 to get down to 12.75? Once, twice, 3 times, 4 times, 5 times, 6 times. You guys can handle that? All right. So take this times by 6. 5730 times by 6 means it's going to take this many years, which is B. Okay. So those last ones were all the half-life type questions. The first one here would have been knowing about alpha, beta, gamma decay. You should also know about that as well. Okay. And then the thing I didn't test you on, at least I didn't have a diploma question to test on, is if they gave you the number of the mass of this uranium, if they gave you the mass of this thorium, and they gave you the mass of an alpha particle, would you guys be able to calculate how much energy was released? Okay. So if those are the 3 things you can do, you've got this unit. Sound good? Okay. One last thought, and then I'll stop for the day here. Tomorrow, what we're going to talk about then is the processes of fission and fusion, which is kind of an extension of this topic. The whole idea of, well, what did the Manhattan Project scientists do when they figured out how to make atomic bombs? How does an atomic bomb actually work? Right? And so the 2 main ways are fission. Fission involves having things break apart, and fusion involves having things combine together. So we're going to kind of build on this and do very, very similar concepts. We're going to calculate how much energy these nuclear bombs can have. Sound good? Okay, one last thought then. Keep thinking of new things to talk about here. After May Long Weekend, when we come back, the last thing we're going to learn about is antimatter and quarks. And so I'll kind of talk more about stuff that I skipped over today. Antimatter is like the negativized version of regular matter, and quarks are like the smaller than subatomic particle stuff. And so we'll briefly talk about that stuff there, and it's very strange. I mean, very similar to the whole quantum stuff. I don't fully get this stuff. I mean, this is what modern physicists are working on, is antimatter. How do you test for antimatter? Like, where do you find it? So, and that's it. Then we're done our course. Okay, any questions? You guys good? Okay, so you have 5 things to do in this unit. A video assignment, which hopefully you're done, close to. A regular assignment, a timeline, and then when we come back from May Long Weekend, we're doing a quiz and a unit test. And then we're into review. So we should be done by early June, which is awesome. Sound good? Cool. Okay, you got about 15 minutes to work on whatever you have few minutes to do. So let me know if I can help with something.